like super interesting and definitely something that is very valuable for the blockchain ecosystem. So yeah, this is like sort of joint work with a bunch of folks at Jump, Manuel Sena and like Nick Stalder in particular, who helped like kind of lead and spearhead the development effort on the software side, and then on the hardware side, Kaveh Sarai, who is like one of our sort of like main FPGA engineers. He's done it, spent decades in this space and like has come up with a ton of clever optimizations to make this work. So cool. So I kind of want to just outline a few things that we're going to talk about today. So first is like the motivation and the application. So why are we doing this in the first place? Why is it important? What kind of applications can it help spur? How is this going to impact, infrastructure, blockchain? Ooh, happened there. Great. And then we're going to go through the theory, what kind of algorithms did we develop? Like, what does the system architecture look like? And then we'll kind of dig into it, what the FPGA implementation looks like, and then kind of think about just in general, like hardware and ZK. Cool. Let's move on. So I think So I think, one of the main motivations for doing acceleration of zero knowledge proof systems on hardware is really because we want to develop something similar to like proving as a service, right? Like if you guys think about like Web 2, there's infrastructure tools, there's services that you can use. You can spin up an EC2 instance, you can go to Amazon, you can say, I want computation as a service, and you can spin something up, you can run complicated machine learning algorithms on there. And that sort of spurred the whole development, right? And the usage of ML algorithms in lots of different applications because there was this infrastructure layer that was set up already for you to do things like this. We want something similar for zero knowledge proofs, right? Like, I think in particular, like one thing that we've talked about a lot, we've talked about in the panel earlier on this as well, is like the importance of ZKs. And like if ZKs are going to become an important primitive in the blockchain ecosystem, we want them to be readily accessible to people, right? And so like trying to generate a zero knowledge proof on your iPhone, trying to do it on your laptop, on your MacBook is hard enough. And so we want to make it as accessible as possible to as many people as possible. And so the way that we sort of thought about this is like, you have clients, they request some proofs, you have a network of provers that are running, and those provers are going to generate proofs on demand for you. You're going to maybe pay them some fee, and then they're going to match that fee. And you create this sort of marketplace where there's a prover network that's generating proofs, and then they're ordering these proofs in a way, such a way that it makes it accessible for people to use in all sorts of different applications. It could be rollups, it could be trustless cross-chain bridges, it could be all sorts of things that you want to do with zero knowledge proofs. So the main question is, this seems like a really complicated thing. How do we actually get there? How do we get to building, zero knowledge proofs as a service? So I think the main thing that we have been sort of focused on is like kind of optimizing the most general components of a proof system. So if you take something like, a snark that I put up here, like a pre-processing snark, if you don't know what that means, like don't worry about it, but there's like sort of two main components of it. Polynomial commitment schemes, and then the interactive like Oracle proof that kind of like lies underneath, right? And so, oh great, Kaveh's here too. Okay. So I think like if you go down to the lowest level components, that's where you're going to get the most generality, right? Like if you look at the components of the proof system that are going to be available across multiple different proof systems. So whether or not you're using Karatsuba, if you're using Plonk, if you're using all these other proof systems, like what is the thing that's going to help accelerate all of them? And then that's what we're going to try to bring to proving as a service. So I mentioned a couple of things here, like what do these components look like? One of them is multiscalar multiplications. The other one might be like number theoretic transforms. And then finite field friendly like hash functions. And then underneath those, you have like optimizing elliptic curve operations and finite field arithmetic. So these are like a few different components that you need. I'll go into more detail on like what these terms actually mean. But these are sort of the important components that I think are most general and the most low level that we can tackle immediately. So what's the goal? The goal is to create a fully pipelined curve operation on an FPGA with efficient scheduling. What does that mean? So it means like we want to be able to leverage the parallelism of the FPGA and the hardware as much as possible, while also like having an efficient scheduler from the CPU so that we can communicate effectively with our hardware device. And so if we can do that, we can get like a bunch of parallelism essentially, and then that kind of enables us to accelerate the generation of these proofs. So first, let's dive into some theory. Let's start with like elliptic curve cryptography basics. So this is the shape of an elliptic curve. This is just one form of elliptic curve, the Weierstrass like form. of an elliptic curve. Looks like this, kind of, if you plot it normally. It looks kind of weird, but this is the equation of it. So let's define some operations on this curve. Like let's try to add two numbers maybe on this curve. So let's pick a point P, pick a point Q. Let's add them together. There's some complicated formula that makes this work, but let's just say it's defined, right? Like you can add 2 points on a curve. Okay, this is kind of like this is what the symmetry actually looks like. So this is how you add points. You kind of you draw a line through it. You find the point on the opposite side, and then you can define basically arithmetic on your elliptic curve. So the other other important component of proof systems is like finite fields. So what are finite fields? I'm going to describe all of this at a super high level for folks who are already familiar with this. You're going to be slightly annoyed, but it's this is very hand wavy descriptions of elliptic curves and finite fields. But basically, a finite field you can think of as something that's like a ring over some prime. So some prime number. It's maybe like hundreds of bits wide, like 377. In particular, this is like why BLS 12377 is like an elliptic curve, and maybe you have a finite field defined over a prime that's size 377. So how do you define, again, like operations in the finite field? So any operation in a finite field is going to be like you take some number in the field, you add another number in the field, and then you modulo the primes. Okay, does this work? Okay, cool. All right. Hopefully we don't run into any more technical difficulties, but yeah. So if we define like addition on the finite field, it's going to be like some number plus some other number in the field, and then you modulo that prime. So you can think of it as like a clock. You're just going around the clock so that you don't deal with any overflows. That's basically the idea. And you can define multiplication the same way. You can also define inversion in the same way. And so we just have these operations that you might want to just keep in the back of your head while we're talking about some of this stuff. Okay, cool. So now to the actual thing that they're talking about. What is multiscalar multiplication? So first, there's like scalar multiplication, right? So scalar multiplication is just taking some number, maybe like 5, and multiplying it by some number p, which is like in your elliptic curve. So it's just the number 5 might be represented by some 256-bit number, and then you're going to multiply it, and so you're just adding it repeatedly. So this is like just the definition of like multiplication. Now, multiscalar multiplication means that you have multiple scalars and you have multiple points, and all you want to do is sum them up and get some results. So maybe you have like 5p plus 2p plus 3p, right? So like 5p1 plus 3p1 plus 2p1, and then you want to compute some results. So the end result of your computation is going to be some point in this group, this elliptic curve. So kind of want to describe like why MSM is difficult in the first place. Like why isn't this like a solved problem already? Like why are people working on this and why is it interesting? So there's just really not like a lot of structure to the problem. So you have like random scalars. This is sort of the equation that I just showed on the last slide. But there's not a lot of structure to this problem. Like you just have random scalars that are in some prime field that I talked about, like some finite field, and then you have a bunch of random points that are from the elliptic curve, and you're told, okay, compute this fast. Like how do you do this? Right? There's no like structure to the problem. You're just receiving random inputs, and then you need to compute some output. And so it seems at first like, how do I do any of this? Like there's no reasonable way to actually find some clever trick to compute this efficiently. But there are ways to do it. And so like just to illustrate the complexity of the problem, I kind of want to just go through this diagram. I don't look at it too heavily, but I'll just kind of introduce it. So we're trying to do basically multiscalar multiplications where you have like 2 to the 26 points and 2 to the 26 scalars. So that's the order of the problem first. So that's equivalent to about 64 million points and 64 million scalars. So for each one of these scalar multiplications that's in this multiscalar multiplication, you have to do like hundreds of different point adds. So what I showed on the slide about elliptic curves, like where you add 2 points together, you have to do hundreds of those. For each point add, you have to do like 10 modular sort of like field multiplications, so multiplications in the field. Then, if you use some other representation, like if you do some tricks, you might have to use, that might like scale to like 3 multiplications in the field. And then each of those multiplications is actually in hardware when you try to implement it, right? And like even in a CPU, like those are 400-bit wide like multiplications. So you're dealing with like multiple levels of, nested, you can imagine it as like nested loops. Like what is the complexity of the problem? It's like 100 times 10 times 3 times the number of multiplications that you actually have to do with the number of bits. And then once you do that, for all of these, for each one of these like scalar multiplications, you have to aggregate all these points. And that's 64 million, points that you have to accumulate at the end. So this is not like an easy problem to do by any means, like in like traditional hardware. So visually, this is sort of, this is kind of what it looks like. This is just a diagram representing, basically the 3 levels of optimization that we've looked at, right? It's like one is doing MSM. So maybe you have the algorithmic side, which is like, I want to figure out how to parallelize some of these optimizations. So I'm going to use an algorithm that helps us create some sort of parallelization. Then you want to, you might want to think about your curve operations, like what operations you're actually doing on the elliptic curves. And then the third one is like the actual field arithmetic that I mentioned, which is like, the modular field arithmetic in the previous slide that you saw. And you can sort of decompose the problem visually like this, where you have, a bunch of different columns, and you're trying to process these columns in parallel and then aggregate them. So I don't know if Kaveh can you hear him? Yeah, can you try and speak, Kaveh?
Can you hear me?
Oh, he's very quiet, but yeah.
Is it too quiet?
Yeah, can you up the volume on? Can you try to up the volume on the Zoom so we can hear him?
Can I do that, or is it like
Yeah, Kaveh, can you keep trying?
I don't think I can increase the gain on my microphone.
Oh, okay. Yeah, I think we can hear him, right? Is that good?
Am I good now?
Yeah, we can hear you, Kaveh. So
Okay.
yeah, this is Kaveh, one of our, that I mentioned who's like one of our FPGA guys. So yeah, if you want to take it from here, go into some more detail.
Yeah. Hi, everyone. So yeah, we have a very complex set of operations that we have to do, and the simplest form you can perform a multiplication, like a scalar multiplication by a point, is you just basically try to add the number to itself, right, n times, and that's very inefficient, especially because n in this case is like 256 bits wide, so that can take a while. But what you can do is use a method called double add, and what that means is you represent the number n in its binary form, and what you see here is the top vector of zeros and ones. Assume that's the binary representation of the n, and you start from the right, as in like the LSB, the lowest significant bit of a number, and every time you see a 1, you add your running accumulator to your other accumulator. So you basically start by 2 accumulators. You have an ACC and a Q, and every step that you go to the left, you're doubling your Q. You start by P and you keep doubling it. And why double? Because you're working in binary, right? So you're every time it's a power of 2, so you have to add to it. So you just double it every time. And if you see a 1, that means that bit is required. So you add that to your accumulator. If you don't, you skip it, but you still have to double, right? So that means overall, you're going to double Q 256 times. You may add also in the order of 256 times to your accumulator, but you may not, depending on the number of ones and zeros you have. Well, these are supposed to be random, so you can guess half the time, half the bits are going to be 1. So you end up in the order of 380, 400 times of adds. And I should mention that when we say double is really an add, right? So you're just adding Q to yourself, and that's still a very expensive operation on the elliptic curve.
Yeah, the sort of important thing to mention here is that the complexity of doing like double and add is really like, the number of bits in n, right? So if n is like a 256-bit number, the complexity of like actually doing this, like, and when I say complexity, like sort of algorithmic complexity, is like, on the order of like 256 bits. So this is like not really that optimal because you're doing so many different operations as a result of the length of the bits that you want to process. Yeah, so there are some other techniques. I can actually do this one. So yeah, I think so NAF is this other sort of redundant bit representation. So you saw on the other slide, like take any binary representation of a number, it's going to have half ones and half zeros, right? In an expectation, it'll most on average we'll have half ones, half zeros. So how many ones do you have to process essentially is going to be the question. So in non-adjacent form, it's just some redundant bit representation. It allows you to represent a binary number. Instead of 0 and 1, it's 0, 1, and negative 1. And so you get sort of the Hamming weight of this is 1/3 instead of 1/2. So you have less ones to process. And because you have less ones to process, the complexity of this becomes lower. The idea is basically that you can't have two consecutive ones next to each other, or two consecutive ones and negative ones next to each other. And so it turns out that this actually, there's some equivalency between binary representation and this representation. And it reduces the number of adds from n/2 to n/3. So that can help. Yeah, so another thing I think we mentioned earlier was coordinate systems. So talked about there were 3 levels of optimizations that we looked at, right? So one was on the algorithmic side. The second one was looking at different coordinate systems and actually looking at the elliptic curve. What properties of the elliptic curve can we leverage to make this problem more structured and therefore find ways to optimize this? So it's a bunch of different coordinate systems. There's the affine coordinate system. It's defined as follows. There's some complicated formula for it. You can look it up for whatever curve that you want. The key thing to mention is affine maybe has 3 multiplications of the actual finite field elements, and then it has 1 division. So there's other coordinate systems, projective coordinates, which have maybe 14 multiplications, but they have 0 divisions, right? And the reason I mention these is because multiplications are they're particularly easier to do in hardware. Divisions are really hard to do. So multiplications really aren't as hard. So it makes sense maybe to convert to a coordinate system where you don't have to do any divisions. There's also other ones like Jacobian. There's 16 adds, there's 6 doubles, there's all sorts of different coordinate systems that you can choose. And I won't mention the one that we've used and because we're actually competing in a prize and we'll release these our design fully in about a week, but I won't tell you what the coordinate system is that we used for now. So okay, so how do we do MSM with double and add? So we know how to do n times p that we showed, 1 scalar multiplication. So can we do the MSM? So what Kaveh was talking about was with n equals 256 and the number of multiscalar multiplications, so the number of points that we have, which is 64 million. A naive sort of implementation of this would cost 377 times 377 which is the order of the curve that we're working with, right? Which is the type of curve we're working with. And then with NAF, you can bring it down to 280. You can do some other optimizations, kind of bring it down to 200, but the complexity is still O of 200n, right? It's not great. So we need to be able to reduce that constant as much as possible. So one way we can do this is use the bucketing method. People who are familiar with the field will probably know this. It's pretty well-known algorithm. It's also known as Pippinger's method. The idea is you want to create some level of parallelization without actually having parallelization in the problem itself. So so now the bucket method actually can bring you down to order 16n, 16 to 17n, and then I'll let Kaveh go into this in more detail.
All right, yeah. So so the idea behind the bucket method is imagine. So the idea is instead of doing the multiplication by a scalar, you don't. That's the idea. You don't do the multiplication. So imagine if the n, our scalars were only 3 bits wide, right? I mean, of course they're not, but for the sake of example. So we have 3 bits. Let's say we have 4 3-bit numbers here, and we want to multiply them by 4 points. And by the way, this only works when you have multiscalar multiplication, right? There's no discernible benefits when you have only single scalar multiplication. So I want to multiply these numbers, these scalars, by 4 different points. And instead of multiplying them, I'm going to allocate a bucket for every possible number that I can have as my scalar, right? You can already see that this is absurd, but right? For small enough width of a scalar, this actually works out, right? So for 3 bits wide scalars, I can allocate 8 buckets, right? 0 to 7. And as every time that I wanted, I'm just going to walk through all these numbers in a column base, right, from top to bottom. And then I'm going to say, look, I'm multiplying 2, that's 0, 1, 0, right? Multiplying 2 by P0. What that means is, instead of actually multiplying it, I'm going to put P0 into bucket 2, right? And what do I mean by putting a number in there, right? That means I'm going to add P0 to that bucket. So a bucket is basically an accumulator, right? And next number is 7. I'm going to put it in bucket 7. Third number is 2 again. So that means I'm adding it to that bucket, to that accumulator, right? And then fourth number is also 7. So the 4 of them at the end are placed and added properly in the corresponding buckets, right? Okay, so now I have these buckets. What am I supposed to do to have a final multiscalar multiplication out of these? So what I need to do is, bucket 7 is positioned in the final result is 7 orders of magnitude to the left, right? Bucket 6 is 6, right? So what I need to do is I need to add bucket 7 to my final result 7 times, because it's really everything that's in that bucket needs to be multiplied by 7. I haven't done the multiplication right? So what I do is, if I start from the biggest bucket, like bucket 7, and put that into my first accumulator, and then add that to my second, like the result accumulator, we call that R in that equation at the bottom left. And I walk through the buckets. So I go to the next bucket, bucket 6, and I add that to my first accumulator. Now what's in my accumulator is 6 and 7. If I add that first accumulator to my result again, my result now has 1 6 and 2 7s in it. Now imagine if I do this 8 times, my result will have 7 7s, 6 6, 5 5, right? But the nice thing is I only went through this one time, right? So it's a linear complexity of in terms of the number of adds that you have to do. It's like 2n, but you end up with really multiplying all of your buckets with their corresponding index, right? And that's the very nice thing about it. Well, what's the problem with it? Well, your number is 256 bits wide, right? 2 to 256. You cannot afford to have that many buckets, right? But you can actually maybe do something about it. So the next slide, yes. So imagine if our scalar was now 6 bits wide, right? So we can break down the scalars into multiple columns and of 2 bits wide each. And then for each column, you would allocate a set of buckets. So you can see I have R0, R1, R2 now, right? So same deal for every column. You just walk through it instead of multiplying so what we call when we break down a number into smaller width numbers, we call them limbs. So instead of multiplying those limbs with the corresponding points, we just basically take the point, put it into a corresponding bucket. And at the end of the day, we end up with 3 results, right? Now we need to add them together. What does it take to add them together? Well, R0 is in the right place. R1 needs to be shifted 2 bits, right? Because that's its rightful place. R2 needs to be shifted 4 times. So each one of those, they have to be added double the number of bits that it takes to go into the right order. And then you just simply add them all up. So you end up with in the order of, if your scalar is 256 bits wide, you end up in the order of 256 number of doubles, and the number of columns that you have, you just have to add them all, right? So because we have a nice number of 256 bits wide, if you conveniently choose limbs of 16 bits wide, you end up with also 16 columns. And 16 bits means you need 64,000 buckets. That's not on the high side, but it's in this day and age, you can actually fit that many, on the FPGA. So we can actually afford that. So we can do 16-bit limbs and 16 columns. And what that means is you run through the column, you end up with 16 numbers, and you have to double, 256 times, and then you add them all up with 15 operations. That's 16 minus 1, right? And so it's a fairly better algorithm compared to double add of all the 2 to 226 numbers, right? Yeah,
Just
I'll
at a
hand
high
it back
level.
to you.
Yeah, just at a high level, I think like in the diagram that you guys saw earlier, like instead of processing these sequentially, you're doing, each column in parallel. And so that's where you're getting the parallelism from, where instead of doing 256 sequentially, you're getting, maybe 16, right? So you might create 16 columns, and so you can process these columns individually or in parallel, and then you can reduce the complexity down from like 256 down to 16. Cool. Yeah, this is just bit more in-depth description of like what the complexity looks like with if you set the limb size to be 16. Cool. Yeah, Kaveh, you want to do this as well?
Absolutely. So, so what does it look like from a high-level perspective? So you break it down into multiple columns. In each column, you have to accumulate all of the points into their corresponding buckets, and you basically end up every time that you look at the limb of that scalar for the corresponding point, and you grab the point, you'd add it to that bucket, which is really an accumulator. And at the end of the column, you have to aggregate all those buckets together, right? So basically, it only takes it's a linear complexity, right? So you only have to do it with 16-bit wide scalars. You end up doing that 32,000 times, and you do have to shift the result. Like, remember, we have as many columns as results, and each result has to be shifted in its place, and the shifting is done by doubling itself, the number, right? So you end up doubling the number, like maybe for each column you end up doubling it as many as its index, and that's it. And then you do 15 like C minus 1 basically adds to add them all up together, and you have your result.
Cool. Yeah, so maybe we'll talk about like what why the FPGA is like useful in the first place. So I think like in general, like the FPGA is slower than the CPU. Like it runs at a lower clock frequency than the CPU. But the idea is that if you're able to pipeline all these operations, right? Like meaning that as soon as you send one operation to the pipeline, you can send another one. And so once you can do this, you can sort of if you can initiate every operation at like 200 megahertz, for example, every 5 nanoseconds, like you can get a ton of parallelism in your system. And so the idea is like you implement a full curve operation on the FPGA, like one of these point adds, and you do this full MSM like on the FPGA, then it shouldn't take too long to do, right? So that's the idea. And like we'll like publish these results as well, but we're like fairly certain that this is like pretty optimal, and that we can get somewhere on the order of like actually I won't mention the exact number right now, but it's I think it's like a lot higher than I think exists in the literature today in terms of speed. So and there's some other things that we can do as well. Maybe we can put 2 curve ops on an FPGA, so like 2 full pipelines. We can up the frequency, and we're very concrete about these numbers. I think I think Kaveh will tell you like upping the clock frequency on an FPGA is not easy, and there's a lot of literature that kind of abstracts away from that complexity and says that given that we can up the clock frequency, we will do well. And I think that's like that doesn't give you a good measure of like concrete efficiency. So do you want to add anything to that, Kaveh?
Oh, absolutely. So I guess I want to add to that the pipelining. It's very important to understand the difference here between the FPGA platform and the processor platform. That in a processor pipeline, when we talk about pipelining, right? In a processor pipeline, it's the same terminology, but what's really happening in that pipeline is the data of the operations are sitting in the memory, right? And what flows through the pipeline is instructions, right? In a pipeline architecture on the FPGA, it's exactly the opposite. You have the instructions fixed into the pipeline. So every physical location of the pipeline is specialized to do a specific task. For example, one of those modular multiplications of the curve operation, or maybe one of those modular adds, or so maybe an if statement. And what you feed through is the data. So the data moves through instead of the instruction, and that's why we say every 5 nano, or whatever the clock period is, we can initiate a new operation, because these data, they literally walk through the pipeline. So the first stage of the pipeline is not occupied by the previous operation anymore. So you can actually place a new data for a new operation in that first stage. And then they basically walk through the pipeline every 5 nanos. And that's how you get the massive parallelism that you from the pipeline. Yeah.
Cool. Yeah, so we just talked about some of the theory. We talked about, like how does this, how this might work. How do you actually put this on an FPGA? Yeah, go ahead, Kavik.
Right. Yeah, so what we really want is we want to have a fully pipeline implementation on the in hardware. Every time, even if it is 2-cycle delay to initiate an operation, that's like half the throughput. So we really don't want to compromise on that. So we're basically aiming for a fully pipeline implementation of an add operation. And when you think about it, everything comes down to adding 2 points together. Like that's the basic operation on the curve. And depending on the coordinate system that you're in, you may have to, there might be some minor differences between adding a number, like adding 2 distinct numbers and adding to a number to itself. So there's like some complexity there as well. But when you look at the operations involved, if you're not in affine coordinate system, it really comes down to multiplication. Inversion is kind of tricky. Like it's a multi-cycle operation, so it's probably not going to happen. But for any other project coordinate system, you basically have a lot of different multiplications. And even when you're talking about modular multiplications, at the bottom of it, it really is a wide multiplier. So you're constantly multiplying 377, or sometimes even wider numbers by each other. Now, keep in mind that not just FPGAs, any hardware you see out there, they're not really optimized for such a wide numbers, right? The FPGAs in particular, they have multipliers, but they're very tiny. Like they're like 18 by 27 signed multipliers. So you really have like 17 by 26 unsigned multipliers. And like on your Xeon or AMD processor, you generally have like a 64-bit multiplier. And on GPUs, you have even smaller multipliers, right? Because that's how they're really tuned for graphics processing and tensor. So these days, everyone in the other in other domains, like in the AI and all that, they're moving towards narrower and narrower data points. But in this field, doesn't seem to be any movement of going any narrower. So we're kind of stuck in this in this domain that we have very wide numbers, and we have to multiply them together. And it's not just 1 or 2 multiplications. We have to do in the order of 10 multiplications, 10 to 20 multiplications in the pipeline. And when you look at it, when you put it all together, you realize that even 1 multiplication is a massive circuit. Now, these FPGAs, the modern FPGAs are big. They have in the order of 1 million LUTs and like 2 million registers and 20 megabytes of on-chip SRAM. They're actually um, they have a very nice size in terms of like capacity, but what's this multiplier is also very, very expensive, like it's very large. And interestingly enough, what you end up seeing happening is when you design a multiplier out of these smaller multipliers, you end up consuming so many wires. And the reason for that is you're just basically connecting up so many smaller components together. And these are very wide numbers. So you're just shuffling a lot of bits around. And funny enough, you actually run out of wires before you run out of logic. Like you run out of lots or memory or registers or any of that. And yeah, so that's the biggest challenge. It's like, how do you come up with a multiplier design that is not really optimized for logic, it's optimized for wires? And that's a very challenging and interesting question. So maybe we can go to the next slide. Yeah. So I mean, everyone knows this, like in kindergarten, no, not kindergarten, but maybe maybe elementary school.
It was for Kaveh.
And yeah, so if you have two numbers, A and B, right, and if you want to multiply them together, usually what we do is we look at digits, right? Well, digits can be limbs, right? You can look at it as like multiple bits but partial bits of the number. So if you break it down in half and you want to multiply them together, what you do is you do all the crosses, right? All the limbs, they have to be multiplied by each other. What happens is, this is nice and all, like you just broke down the problem in half. Okay, great. But you're doing four sub-multiplications, right? Someone called Karatsuba came in, and if you go to the next slide, and he realized that if you look at the right side, we are doing the crosses, like as in like A0, B1 and B0, A1 independently, but we don't really need the partial multiplication, right? What we need is the sum of those, like sum as in SUM, right? They added partial multiplication. We don't really care what B0, A1 is, right? And why is that? Because they get added in the same shift position. You see how they're shifted in the right place? They're all shifted to the same, because, it's the same limb size, right? And so Karatsuba realized that if you multiply, if you add the limbs together, funny enough, right? And then you multiply, that gives you the partial multiplications added together. But the problem is it gives you two extra terms, which is A0, B0, A1, B1, right? Which is included in that middle shift position, right? Well, then the nice thing is you have to calculate A0, B0, and A1, B1 anyways, right? So you might as well just subtract those from that, and you get your result. Now, okay, so what's the trade-off here? The trade-off here is you are doing 3 multiplications, right? So that's nice. But now you have 2 subtractions, right? Well, when you look at it, these are, I mean, from naively looking at it, you would think that, yeah, okay, I just saved the multiplication, right? But these are wide numbers, right? Those subtractors are not cheap either, right? And there's another problem with it, and you can see it in the picture that when you add the limbs together and then you multiply, you end up with a wider multiplier because now you have a carry, right? So that's not trivial to deal with, and it needs special attention. And so it's basically trade-offs like this that you have to basically, exhaust your search space to see what really works, what doesn't, what consumes, what minimizes number of wires, what minimizes logic, maybe, and what works best for your FPGA or other hardware platform. And is this it? No, there's you can actually do you can actually divide your numbers into more limbs. If we go to the next slide, there is So Toom-Cook came along and they realized that Karatsuba actually stumbled upon a very special case of a generic case of breaking down a number into n limbs, and it doesn't even have to be symmetric. So you can break down one number into m limbs, the other number into n limbs, and you can actually start saving more and more submultipliers. But the problem is they end up giving you a lot of adds and subtractors, and sometimes some of those submultipliers end up not being trivial because again, because of the added carries, and sometimes you have to do multiply by a constant that is not really friendly in hardware, like for example, multiply by 7 or stuff like that. So again, this is not helping, right? This is only adding to the search space. Like you have to search all the possible ways you can create a very wide multiplier to see what really works in your architecture. Yeah.
Yeah. Just to kind of tie this back into what we were talking about in the implementation architecture. Like this is the part where we were talking about like doing the 400-bit wide like multiplications and finding optimizations for that enable optimizations for the full sort of implementation. And like we tried a bunch of different architectures for these multipliers. So that was definitely an interesting learning experience there. Yeah, so there's a bunch of other things that you can do. Like maybe you can leverage like constant multipliers. So if you run out of like DSPs on the chip, can you leverage like a constant multiplier instead? One of the multiplications that we've been using in the field is like Montgomery multiplication. So that might involve two constant multiplications. Can we leverage constant multipliers in the FPGAs instead of the DSPs? And that might give you some like savings in terms of overhead. I won't go into that in too much detail. Yeah, so this is just a multiplier if you want to multiply A times B. The idea is that if the first bit is set to 1, you shift and then you add. So if this if B1 is 1, then you shift and you add, and so that's how a multiplier is like actually implemented in hardware. And so the idea is that can you just remove all these if statements, like where you check if a bit is 1? You already know that it's 1, so you should just leverage the fact that it's 1 and or 0, and you should just shift correspondingly and add. We'll also won't go into this in too much detail, but you can sort of get the idea that you want to like basically remove as much overhead as possible by using these constant multipliers. So what is the summary of this? We basically turned an unstructured problem into something that looks structured, right? So we took some problem that had these random scalars, random points, and then developed some structure for it. And so the key insight here is that there's this like space-time trade-off, right? So if you break down the scalars into small enough components, you can develop this trade-off of like space and time. And so now you can the bucket method helped you sum scalars, some points with the same scalars. So you would bucket them into the corresponding buckets. Then you would, if you make the scalars short enough, you can put them into these little windows where you're treating them. You can develop these multipliers that actually work well. And then you're actually only multiplying by the scalar once, right? In this method. So you're not actually making multiple passes over the data. And so that helps you, turn it into a problem that's actually suitable for an FPGA or on hardware. Let's see. Oh, there we go. Yeah, Kaveh, if you wanted to add anything on that last slide, but other than that, I think we're done.
I'm all set. Thank you very much, everyone. Yeah.
All right, thanks. Yeah, I don't know if we have time for questions or if anybody has a question. Yeah. Any questions or happy to take any questions also at a high level. I know this is like pretty depth. Yeah. So let's go back to like what we're actually trying to do with this. So like we just kind of went into detail about like one specific sort of implementation of multiscalar multiplications on FPGAs, but that's sort of that's not necessarily like this ties into our broader goal, which is like what I mentioned in the beginning, which is how do we make sort of big infrastructural changes, right? Like how do we bring about these changes so that we can leverage zero knowledge proofs in a way that's accessible to a wide array of people and it sort of becomes like a real primitive that people actually want to use, on a daily basis. Like if I want to outsource my computation, I want to have proving as a service, pass, as they say, like available out there. And I want like a compute platform that can actually serve these proofs to me. And so, we looked at the most general things, multiscalar multiplication and number theoretic transforms, where actually recently we've been working on that as well. And I think like, if there are enough people who can work on this and stand up provers and provide some of this, provide some of these resources to a network and get compensated for it, then the incentive is there, right? For you to actually run these provers, and it sort of becomes, in some ways similar to Bitcoin mining, right? That you're providing a real service, like you're doing real compute that's available to people. And this is something that we've been thinking about for a while, and I think we're gonna try to leverage these in other products, like and other developments. We've been thinking a lot about like trustless cross-chain communication. I think like particular that's going to be very useful. You really need like in cross-chain messaging, I think one of the main things that you're optimizing for is latency. As a user, you want to make sure that like if I'm sending a message, it's going to arrive on some other chain. Maybe from like ETH to Solana, it's going to arrive on Solana, in some time frame that makes sense for my application. And typically that might be like under a second, right? And so one of the main bottlenecks still remains, for zero knowledge proofs is like these proof generation times. And I think we're trying to tackle the toughest problems on the infrastructural level, and hopefully we can make an impact in sort of all the various applications that want to use this technology. So thanks. All right, no other questions then. I think we're good.